Okay, exponential functions. Exponential functions are going to be just like any other function that we've worked with, in the sense that there's going to be an independent and a dependent variable, or an input and an output, an x and a y. And so these functions can model an initial amount which is repeatedly multiplied by the same positive number. So it's going to have this exponential growth factor where you're going to find that the variable is going to be in the exponent. And so exponential functions are just that other group of functions that we're going to do that they have the same characteristics as all other functions. There's transformations, dilations, different characteristics, and manipulations, but these will provide many real-world models and situations that we couldn't if we were limited to possibly just linear functions. So moving forward with exponential functions, identifying linear and exponential functions. Well, we know then when we have a linear function, we are looking at a function where we have a constant rate of change. So if I were to look here real quick, I can see that, just at a quick glance, that this B example, it's y equals 3x. Well, that can also be rewritten like that, and it looks like it's slope-intercept form, and I have a slope of 3, and so that looks like this looks like a linear function to me. Let's see, what else can we determine? I'm going to go ahead and change these tables around so they're a little bit easier to work with. And what I'm going to do here is I'm sort of whittling away at what might be the easiest problems first. And we can see here, if we go to option C here, as my x increases by 1, my y is increasing by 2. So what I see here is a constant rate of change, or my slope is going to be 2 over 1. So it looks like it's a linear function. So again, we have a constant rate of change, so that is also going to be a linear function. And looking at this one, looking at D. D is by definition an exponential function because my exponent is my variable. So that one is going to be exponential function. But we do have a table that we need to figure out what's going on, and I hope that looking at table over here, I've gone ahead and rewritten it 0, 1, 2, 3, and with this, I'm hoping that you can see that, well, the second, third, and fourth, those look like factors of 3 or multiples of 3. So what I can do is I know that I have 3. 3 is 3 to the first, 9 is 3 to the second, 27 is 3 to the third, but we're dealing with a negative number here. I have negatives. I have negative 1, 3, 9, and 27. So we are looking at, I need to do something there. So I think, I was going to try and come up with a formula real quick, but I don't need to. What I'm looking for is that when I went from here to here, I multiplied times 3. When I went from here to here, I multiplied times 3 again, and so forth. So just multiplying by 3, that is going to end up giving me an exponential function, because as my x changes by the value of 1, my y changes by a constant multiple, and this multiple happens to be 3. Okay, so without getting too difficult there, I started to go really in depth with some explanations. Not necessary, we were just looking for that little bit. So as we are evaluating an exponential function, we have an initial population of 20 rabbits, triples every half year, and this function, they've given it to me, is 20 times 3 to the x, gives the population over x half years, so that's a half year. How many rabbits will there be in 3 years? Well, remember that my equation is written in half years, right? So x half years, but they're telling me 3 years. So I need to know that we are dealing with 3 years is going to equal 6 half years, because that's going to go into my formula for x, because x is based on half years. So I'm going to have f of 6, because I'm going to input for x 6. So wherever there is an x, I'm going to put 6, so that's going to be 20 times 3 to the 6th power, and that should tell me how many rabbits will there be in 3 years. Okay, when I put that in the calculator, that ends up giving me 14,580. So we're going to have 14,580 rabbits according to this equation after 6 half years or 3 years. Okay, now what they're going to do is they're asking us to graph an exponential function. And it looks like, what is the graph of y when, or graph of y equals 3 times 2 to the x power? So I'm going to go ahead and create my table and my graph real quick. Okay, so I've gone ahead and graphed this exponential function. Well, I haven't graphed it yet, but I've gone and created my table. I have my input values of x, and I plug them into my function, and then I'm going to get my output values y, and then I'm going to be able to create an ordered pair from that for graphing. So take my x, input it into my 3 times 2 to the x power. So wherever I have an x, I'm going to put in a -2. So 3 times 2 to the -2, that gives me 3/4. And I've gone and I've done this for each one of my values of x for the 5 values that I'm going to go ahead and graph. I've come up with my outputs, and I've created my ordered pairs here, so I'm going to go ahead and graph those. So graphing x, when x is -2, it looks like y is going to be 3/4. When x is -1, y is going to be 1.5. When x is 0, y is going to be 3. When x is 1, y is going to be 6. And then when x is 2, y is going to be 12, which is approximately up there, but you get the idea. So when we're graphing this, it's going to have an asymptote where it's going to get really, really close, but never touch the x-axis. And then we go ahead and connect all our points with a smooth curve. And that is what we have for an exponential function. It will never cross over the x-axis because nothing that we put in there for a variable will allow it to be equal to 0. So that is going to be y is equal to 3 times 2 to the x power. And as you look at it, going from left to right, as we are increasing its exponential growth, and it's going very fast, So there you have it, graphing an exponential function. Let's see here, continuing to graph an exponential function. And what we want to do here is it says this computer mapping software allows you to zoom in on an area to view in more detail. And the function given here is f of x equals 100 times 0.25 to the x power, and that models the percent of original area on the map shows after zooming in x times. So x is going to be the number of times that we are going to zoom in, and it wants us to graph this. So let's go ahead and create our table so we can do some graphing. Okay, so I'm going to computer. We're talking about models the percentage of the original area the map shows after zooming in. Okay, well, I'm going to go ahead and start off at 0 and go, and let's see here. So we have 100 times 0.25 to the 0 power, which is going to give me 100. And that gives me an ordered pair of 0, 100. And then I have 100 times 0.25 to the first. And that is going to give me 0.25 times 100, which is going to give me 25. So I have an ordered pair of 125. 100 times 0.25 squared, which turns out to be 6.25. So I have 2 times 6.25, or 2 6.25 is my ordered pair. 3 So I have 100 times 0.25 to the third power, and then I'm going to go ahead and get this one in here, 0.25 to the fourth power. And that is going to give me approximately, right, 1.56, and the next one will be approximately 0.39, which could be very difficult to graph. But we're estimating here because we can't physically draw something that close with the materials at hand. So I have my 4 ordered pairs, and I'm going to go ahead and make a graph real quick. Okay, so as I go to graph some points, I'm going to have 0 and 100, right? 0. I'm going to have 1 and 25. I'm going to have 2 and 6.25, and then I'm going to get really small, but I'm never going to approach the axis. So as I go to graph those with a smooth line, that is what that graph is going to look like when I get done. It's going to get extremely close to my axis, but not touch my x-axis. Okay, so we're going to also zoom in and out of a larger area on the map, or any given map. And this function, f of x equals 10 times 4 to the x power, models the percent of original area of the map shows after zooming out x times. So x is the number of times that you're pressing zoom out. And of course, we're going to go ahead and graph that function. So my function is 100 times 4 to the x power, and we can, well, if we start off at 1 or 0, we know that we would have 100 times 4 to the 0 power, which is going to give me 100. Okay, and let's see here, if we're zooming in, so 1 is going to be 100 times 4 to the 1, which is going to be 400, 2, 3, so we have 100 times 4 to the second, which is going to be 16 times 100, which is 1,600, and then 100 times 4 to the third, which I believe is 64 times 100, which is 6,400. All right, so as I have calculated my points, I'll go ahead and graph them. And I have 0, 100, which is approximately right there. I have 1, 400. I have 2, 1,600. And then something way up top there. So go ahead and connect my points with a smooth curve. And there you go. That's my exponential function. Or did it even ask me larger area of the map, zooming in? I don't necessarily need to know that I need to connect it with a line. And of course, not to forget my ordered pairs that I graphed on the line, on the graph to your right. There we have it. And now this last part, this is going to be using a graphing calculator. So some of the things we're going to need to be able to do is we're going to need to be able to input these graphs into y equals. And then once we're in graph, you're going to need to be able to calculate. So once we put these functions into the y equals, we're going to need then to hit the blue second button and then trace, and that will give us the ability to calculate. And then when we calculate, we are going to calculate for we're going to be able to calculate for intersection, which is option number 5. And it is labeled intersection. How about if I spell it right? Intersection. And it's going to allow us to find out where these two functions equal each other or where they touch, right? That, remember when we had systems of equations, when a line crossed it, it was considered a solution. So what we're looking for is where they are both going to be a solution. So let's see if I can get this on camera. Okay, so what we're looking for here is that we have input our equations into the, we've gone and placed them into y equals, and now what we're going to do is we're going to be able to graph, and we're going to see where these two equations intersect. So that's the exponential function, and then here we come out with the y equals 5, and we can see that their intersection point is going to be right there, but we can't figure that one out because of the decimal place. But what we can do is come over here and we can calculate. So we can second calculate, and right here it says for the intersection point. So when we intersect that, well, it says first curve, which they're looking for the curve before I get to that intersection point. So I can just hit enter. And then I'm going to move to the second curve, which will be past it. And good guess, sure. And there it is. My intersection point is going to be when those two things intersect. The intersection point would be x is 1.4649735, and y is going to be 5. So that's going to be your ordered pair. Okay, so what we're doing here in this next section is we are learning to be able to put these equations into the calculator to where we can find out where they intersect. And what I have here is I've gone ahead and I've input the two equations into my graphing calculator. I've made them different colors so they might be a little bit easier to see. And so here they are. It's going to be 0.03 raised to the x power, and then y is 5. And so when I go ahead and graph, I can see here that here is my exponential function coming down, and then here is my y equals 5 function, and I'm trying to figure out what this point is right here. So what I can do is I can hit second trace and come down here and hit intersect, and what that's going to do is that's going to allow me to see where the value is, and you can just hit enter 3 times. 1, 2, 3, and there you go. My intersection point is when x is negative 1.336, or we could say negative 1.34. That's going to be the point where they intersect, and then y is going to be 5. Okay, so as you can see here, I've gone in just to input those graphs into the calculator and seen what they look like. So putting them into the into your y equals, of course, and then coming up with the intersection point right here is going to be definitely decimal. So want to make sure it's going to be a decimal, so you want to make sure that you're using your references. And then for the other option, again here I've placed them in the into the graphing calculator and let the calculator do the work for me. And here you go, we have one intersection point right there. And we find out that there's intersection point is, goodness, we'll have to talk about that in a minute. But those are my solutions, so just keep that in mind that you have the same possible solutions. as previous examples.